the beginning, there was darkness, and then, bang, giving birth to an endless expanding existence of time, space, and matter. Every day, new discoveries are unlocking the mysterious, the mind-blowing, the deadly secrets of a place we call the universe. Warp speed, transporters, wormholes, and laser blasters. Science fiction concepts, but are they grounded in reality?
Is there life out there? The answer is yes.
Now, the next generation of physicists work to rewrite the cosmic rulebook.
I can't necessarily limit myself by the physics we know today.
And what seemed futuristic just decades ago may be coming soon to a planet near you.
Someone traveling close to the speed of light can effectively jump into the future.
Next stop, tomorrow. Arriving today as we explore the worlds of science fiction and science fact. Science fiction explores new life, new civilizations, and galaxies far, far away. The fantastic future of flying cars and laser beams still seems like a shimmering mirage of a tomorrow that never came.
Roads? Where we're going, I think we'll still need some roads.
But then there are those sci-fi technologies which may be arriving sooner than you think. Running late for an appointment? Stuck in traffic? Science fiction has the answer for your transportation problems. Simply beam from point A to point B.
The Star Trek transporter is one of those things that any of us who do a lot of flying really wish would just please be invented. But then when you start thinking about the technologies required, it becomes a bit daunting.
On Star Trek, as we've depicted it on the show, the transporter works by taking a person apart atom by atom, converting those atoms into a stream of energy, beaming that energy to the target location, and then reassembling all of those atoms that make up the person at the target location.
As they're scanning the person, they're recording the positions of all the atoms, of all the electrons orbiting the atoms, of the spins of all of the electrons, the wave functions of all of the molecular structures in the body, how everything's vibrating, moving, the velocities. The amount of data is enormous. And somehow they're scanning all of it remotely, and then they're somehow taking and tearing that body apart.
The amount of energy required to turn a human into pure energy would be far more than in the most powerful nuclear weapons that humans have ever made. The process itself would be destructive.
To convert someone my size entirely to energy would be the equivalent 41 times the energy release of the largest nuclear weapon ever exploded on planet Earth. I mean, if you tried to transport me right now, you have to ask yourself.
But what comes out the other side of a transporter beam? Is it you? Or a perfect quantum replica of you?
Are they disassembling the person and reassembling them? Or are they disassembling the person, storing the information, and recreating the person from scratch?
It's an interesting question. Does the transporter actually kill you and then create a clone, or does it somehow preserve you and transport you to another place?
If you're going to say that you're disassembled atom by atom, converted into an energy stream, and then reassembled someplace else, I don't see how that's anything other than killing you and resurrecting you.
It may be a device rooted in science fiction, but the real-world prospects for transporter technology attracted the attention of the U.S. military. The Air Force commissioned a study to investigate the future of matter transmission systems, and, not surprisingly, found a number of roadblocks.
Developing a working transporter is a tough nut.
Among the biggest, a problem you may have struggled with on your home computer. Not enough hard drive space. Forget megabytes or gigabytes. The information created by a scan of just one person would generate billions of terabytes.
One person would take roughly enough terabyte drives worth of storage to fill 500 million Empire State Buildings.
And an implication of storing a person as data is, do you have to teleport them immediately? What if you dematerialize them, store the information, and save it for 50 years, 100 years, 5,000 years? From the point of view of that person, it becomes time travel.
If hard drive capacities continue to improve at their present rate, a drive capable of handling the storage requirements may exist in about 200 to 300 years. A final barrier to creating a matter transporter is a fundamental property of quantum physics, known as Heisenberg's uncertainty principle.
After the original Star Trek premiered, a lot of physicists questioned the transporter technology, and one of the biggest problems with it that they talked about was that it's really not possible to know with complete precision both the location and the momentum of an atom or a subatomic particle.
In other words, the more you know where something is, the less you know how fast it's going, and vice versa.
Take a picture of the merry-go-round. Well, you can certainly see where that merry-go-round is with respect to anything else that's nearby, but the things that are spinning on the merry-go-round are kind of blurred.
If you're trying to reassemble the bits and pieces that make up a quantum image of a just dematerialized Captain Kirk, the last thing you want is Heisenberg's quantum uncertainty.
In Star Trek: The Next Generation, one of our technical advisors, Mike Okuda, came up with the idea of this thing called the Heisenberg compensator, which is the component in the transporter that conveniently deals with that little problem. And I always thought that was a very clever solution to one of the biggest obstacles in building a transporter. The transporter would on occasion break down, and that was generally not good for the person being transported.
If some data were lost during transport and you ended up without eyes or a brain or something, that would obviously be disastrous.
You might lose a bit from your DNA, and while your body has DNA repair mechanisms, that repeated numerous times could lead to cancers, it could lead to deformities, it could lead to all sorts of maladies that you really probably wouldn't want to deal with.
Massively huge supercomputers, Heisenberg compensators, quantum scanning, all part of science fiction. So how do we make it science fact? By getting a little spooky. Einstein famously called it spooky action at a distance. It's the bizarre world of quantum entanglement.
Basically, two particles can interact in such a way that when they become separated, the state of one directly affects the state of the other. And using this property of entanglement, you can manipulate one location to change what's going on in the other location instantaneously.
This is about the single freakiest thing to come out of quantum mechanics. There's no way for the information to travel from the one particle to the other. You can separate them by so much that even the speed of light doesn't allow the information to get from one point to the other when you make the measurement. There's probably 3 people on the entire planet that fully understand this concept, and the rest of us just look at the mathematics and get queasy.
Plans are in the works to test the spooky action of entanglement by transmitting information between the ground and low Earth orbit. the first beaming up in human history. This technology could be put to use in the development of a new generation of supercomputers. Computers that may one day be fast enough to carry out the complex calculations needed for a more sophisticated transporter.
I would use a transporter in an instant if I were assured that I could return home to my loved ones when I so desired. I think it would be a fantastic trip.
In J.J. Abrams' reboot of the Star Trek franchise, the villain used a science fiction staple in a whole new way, using a black hole as a weapon.
I love the new Star Trek movie. I love the direction they've gone in, but the black hole just broke the part of my brain that likes physics.
Black holes are regions in space where matter has been compressed so much that the local gravity is so strong that nothing, not even light, can escape.
If you could drop a black hole into the core of a planet, gone. It would implode. Controlling a black hole is nigh impossible because if you try to manipulate it, you would also implode.
In the Star Trek film, some exotic form of matter that they called red matter was used to initiate the formation of a black hole inside the core of an existing planet.
You aren't generally going to collapse a planet into a black hole using any amount of red slime. This is not going to happen.
Of course, in science fact, we recently had our own concerns about black holes and the possibility that in a quest for knowledge, our planet could be obliterated, sucked into the insatiable maw of a black hole we created. In science fiction, such as J.J. Abrams' first Star Trek movie, a black hole created at the center of a planet caused the on-screen deaths of 6 billion Vulcans.
That planet would become part of the mass of the black hole. It would be ripped to shreds and disappear from our universe forever. So it is kind of the ultimate doomsday weapon.
In science fact, plans to smash subatomic particles together here on Earth raised fears that if the particles were going fast enough when they collided, they could form a black hole, destroying our planet.
The new facility that's been built by CERN in Switzerland, the Large Hadron Collider, is designed to explore the fundamental nature of matter, to smash atoms together so that you can break them apart and see what the fundamental building blocks are.
For example, they want to find the so-called Higgs boson, which is thought to give mass to all other particles. But they also might produce miniature black holes.
Black holes on Earth? Humans tend to view black holes as large, swirling, matter-sucking vortexes from which nothing, not even light, can escape. The idea of one forming in Switzerland set off alarm bells. But scientists assured a nervous public any black holes formed would be microscopic.
Tiny little black holes would instantaneously evaporate, yet nevertheless would exist for a very, very short time.
Probability of that happening is small, and even if we did create a microscopic black hole, it's not something that would sink to the center of the Earth and start devouring our planet from the inside out.
How does a black hole grow? Think of a paper stick going round and round on the inside of a cotton candy machine. As the stick gathers material, it grows bigger and bigger, just as a black hole does when it sucks in matter. But a microscopic black hole? The first thing that happens is it eats the stick. Very, very slowly.
And in fact, In the course of a year, a hungry, angry little microscopic black hole might eat 100 protons.
And with the stick going away, with the vortex evaporating faster than it can suck in new material to grow, the microscopic black hole simply disappears.
Black holes aren't something that we need to worry about. In fact, there's a supermassive black hole sitting right in the center of our own Milky Way galaxy, minding its own business with stars happily orbiting it round after round after round. You can actually see around the black holes in some of the nearby galaxies, disks of material getting destroyed as it spirals in. And it gets so hot and so dense as it spirals in that it gives off massive amounts of light.
If sci-fi writers want to make use of black holes as the bad guy, there is a scientifically accurate way to do so.
One of the interesting plot devices that isn't used enough, in my opinion, is the black hole as destructor of the solar system. There could be some small black hole out there on a collision course with our solar system. And we wouldn't see it until it started to interact with the Oort cloud, the cloud of frozen stuff that comets come from in the outer solar system. It could just be on a collision course waiting to destroy our entire solar system, invisible until a few years away from the Earth's doom. The first thing we'd probably notice is the Oort cloud starting to flicker with high-energy particles as little bits of ice start to get sucked in. Then we'd start to notice the outer solar system's orbits getting deformed. And then the amount of deformation of orbits would increase as our own planet Earth, depending on which side of the sun the black hole was coming in from, either started to get pulled toward the sun or pulled out from the sun, causing us to die either by fire or ice. And I personally don't think either is nice.
The destruction of the Earth is a popular theme in science fiction, with threats to the planet's existence coming in many forms. Take the movie Armageddon. An asteroid the size of Texas is bearing down on our planet. In this disaster movie, it's the science which is the real disaster.
I think any scientist will agree that Armageddon, oh my gosh. Science fiction, name only, a lot of fiction, not a lot of science.
The way they depicted this asteroid that was going to impact the Earth and how they dealt with that threat by sending up a space shuttle and using nuclear devices was ridiculous.
The problem with that is now instead of having one asteroid that's going to destroy one part of the planet, you have thousands and maybe millions of chunks of asteroid that are going to destroy large parts of the planet. Yeah, blowing up asteroids, really, really bad. You want to move them somehow, not blow them up.
But if Earth bites the big one, we'll need a new place to live.
The idea of terraforming is you take a world like Mars that isn't currently capable of supporting life just walking around on its surface, and you alter the environment, you alter the planet itself in a way that allows human life to exist casually on the surface.
Make Mars into a place where we can breathe without a spacesuit, where we can stand outside in our comfortable summer clothes and create a whole new world for us to live on. This would be a pretty phenomenal thing to do, but they think not impossible.
A new planet in our solar system for humans to call home, just in case the Earth gets all used up. If our survival as a species depended on it, just what would it take to turn the red planet blue? Mars is a red, barren, desolate world. Freezing plains and sheer cliffs. A permafrost layer embedded in the surface. Massive volcanoes. And dry riverbeds that hint at the planet's watery past.
Because Mars is so similar to Earth, the idea of terraforming Mars has come up in science fiction for decades.
But to make Mars live and breathe again, this frozen wasteland will have to undergo a massive global warming.
A key ingredient for terraforming Mars is to get all the solid carbon dioxide, the dry ice, out of Mars's soil and into the atmosphere. That would create higher pressures. It would also produce some greenhouse warming, raising temperatures. That would go a long way toward making it more sustainable for life.
One of the polar caps of Mars is comprised mostly of frozen carbon dioxide. If we could somehow heat up that polar cap and release that carbon dioxide, put it back into the atmosphere, then you would start a process of thickening the atmosphere of Mars. That would be the first step toward terraforming it.
One way would be to put up a bunch of satellites that would collect the sun's energy and focus them in on Mars. That would basically be absorbed by the surface. It would go into evaporating those ices, would free them up so that they form atmospheric gases. One could also put a bunch of dark material on the frozen polar ice caps of Mars. That dark material would absorb rather than reflect more of the sun's radiation, thus allowing that material and the ices underneath to heat up and evaporate those ices.
When terraforming Mars for human habitation, there's one key ingredient you can't overlook.
Earth has a fairly strong magnetic field. That magnetic field protects us from solar wind. Charged particles streaming out from the sun are shunted around Earth by Earth's magnetic field. Mars doesn't have that. Anybody who tried to live on the surface would have their body, their mass constantly impinged upon by radiation from the sun.
Taking a vacation trip to Mars is still science fiction. But mankind continues to draw closer to the day when ships from Earth will zip around our solar system.
It's relatively easy to get around within our own solar system. 40 years ago, we traveled to the moon. We've sent spacecraft to all of the other planets in our solar system. The distances are measured in millions or billions of miles.
That's local space travel. Interstellar travel is something much different.
One of the very real problems that physics gives us is the limitation of the speed of light.
When it comes to faster than light travel, traditionally, physicists have been speaking with one voice. No way, so say we all.
But why is the speed of light a universal speed limit? That's what one of our viewers wanted to ask the universe. So they wrote to us on our website, why can't something travel faster than the speed of light?
Well, a lot of people ask me that question. It's a favorite. You just can't get from here to there at a speed faster than that of light unless you're massless.
One of the problems we have to figure out how to deal with is as we go faster, essentially our mass increases and it takes more and more energy to increase our velocity.
Only light, photons with no mass, can go at the speed of light. But anything that has mass would require an infinite amount of energy to get going that fast. It can't be done, it's impossible.
In science fiction, this isn't a problem. Just invent some handy bit of futuristic tech to deal with it.
What are dilithium crystals for? What aren't they for? Dilithium crystals make the warp engine go. That's all we need to say about it.
There are various names that have been given to these kinds of technologies. Hyperdrive, superluminal drive, stargates.
More and more, scientists who've grown up watching their heroes whiz around the galaxy seem unwilling to flatly dismiss the possibility of faster-than-light travel.
A scientist named Miguel Alcubierre came up with a theoretical notion for a warp drive that would involve expanding space behind your starship and contracting it in front of your starship. And there was nothing in physics, in Einstein's theory or anybody else's, that says that space itself cannot stretch or be squeezed faster than the speed of light. In fact, we think that's exactly what happened when the universe was born. Space expanded much, much faster than the speed of light in the microseconds after the Big Bang, leading to the universe that we see around us today. So if you had enough energy, you could conceivably expand space behind you at 100 times the speed of light, squeeze space in front of you at 100 times the speed of light, and in effect be traveling at 100 times the speed of light, even though in your own little bubble of space, you're never traveling faster than the speed of light.
When a real-life astronaut wants to get somewhere in a hurry, the options are rather limited.
Most spacecraft today use liquid fuel and solid fuel. The space shuttle uses solid fuel boosters that are kind of like a big bottle rocket. Once you light them off, they're going. On the other hand, you also have chemical rockets. A very simple type would be liquid hydrogen and liquid oxygen. You just run them together, huge amount of energy. The byproduct's water, and a whole lot of heat.
Now, the latest generation of deep space probes relies on entirely new technology. Lifted straight from the pages of classic sci-fi stories, ion drives.
This is where you basically take atoms, strip off a few electrons, and you end up with a charged particle. Accelerate it with a magnetic field, and send these high-velocity particles out one end of the spacecraft.
The difference between that and chemical engines is that with an ion engine, you have very, very low thrust. An ion engine generates the same amount of thrust as the weight of this piece of paper, but it does so for months at a time. And with constant, albeit small, acceleration for months, you can get up to some pretty high speeds.
NASA's Dawn spacecraft is using ion power to close in on an encounter with Vesta and Ceres, two of the largest objects in our solar system's asteroid belt.
One of the things that makes ion drives so powerful is they have the most effective use of fuel. And in space, there's no friction. There's nothing to slow you down. And so all the energy used to accelerate these ions can go into forward velocity. And you can just keep, over huge periods of time, accelerating and accelerating and accelerating.
Traditional chemical rockets burn fast, loud, and hot. Ion propulsion systems, on the other hand, are in it for the long haul.
So ion drives are both science fiction and, today, science fact.
Between space probes headed out of our solar system and TV and radio waves, which have already left, humans have announced their presence to the universe.
We have sent out missions with records containing the sounds of laughter and the beating of a heart, with anatomical diagrams of men and women. These are physical ambassadors that we've sent out among the stars.
Carl Sagan asked the question many years ago, who speaks for Earth? Well, ultimately, I guess we all speak for Earth. And I wish we'd been a little more circumspect or a little more thoughtful about the kinds of messages and ideas we're sending out into space with our radio and television programs.
So far, our broadcasts have gone unanswered. But what if that changes? science fiction is filled with tales of what happens when aliens arrive among us.
I think we're going to find life out there, definitely.
And if that happens, do we stand any chance? Or are we destined to be wiped from existence, exterminated by an advanced alien intellect? They say they come in peace. They leave our planet in pieces. Since the earliest science fiction stories, some themes have recurred with remarkable frequency, perhaps none so much as this one: alien invasions.
Alien hordes arriving at the Earth and wreaking havoc. Just from a dramatic point of view, that's inherently more interesting than friendly aliens coming and solving all of our problems for us. Things started with H.G. Wells and the War of the Worlds. And he wrote that novel as a kind of criticism of British colonialism at the time.
The movie District 9 takes a look at how humanity is inherently suspicious and inherently, in many ways, racist against the things that we don't understand. And aliens, well, what do we not understand as much as we don't understand life on other worlds?
Astronomers have long been trying to determine if there's a plausible scientific way to answer the age-old question, are we alone? How common is intelligent life in the universe? The Fermi paradox, named for a question first posed by physicist Enrico Fermi, attempts to illuminate a conundrum about extraterrestrial life.
Intelligent life in the universe is common, then where are they? Well, if they're not here, probably not anywhere. So I think either we're unique, which is in and of itself kind of astonishing, or intelligent life like us is just not that common.
Well, the question can be reversed, why haven't they detected us? And we understand that fairly well. What would broadcast our existence to the rest of the universe is our radio emissions. And we've really been broadcasting in any reasonable amount since about the 1920s. So that means that our emissions, which radiate outwards at the speed of light, have reached about 90 light years. So we have a sphere of 90 light years in radius of planets and stars, civilizations that could detect us. That's not very big. Our galaxy is 100,000 light years from end to end. So if there were hundreds, thousands of civilizations out there, it might be that only one or two have been able to detect us in the time we've been broadcasting. And they may not have had time to send a hello message back.
Another possible problem, loss of signal. As radio waves spread out from Earth, they fall off in intensity, eventually blending into the cosmic background. If someone on another planet is going to hear our transmissions, they might have to be relatively close. So how many civilizations might be tuning into our radio shows and reruns? That's a question astronomer Frank Drake famously tried to answer.
About 50 years ago, Frank Drake, a radio astronomer, was considering the possibility for life in the universe, and he launched the first SETI program, the first attempt to use a radio telescope to listen for signals from other stars. So Drake was wondering, well, what are my chances of success here? How many civilizations might there be in our galaxy? So, like any good astronomer, he did a little back-of-the-envelope calculation, and he created an equation that basically said, all right, here's how we calculate the number of civilizations in our galaxy. How many stars are there in our galaxy that are capable of having planets that are like the Earth? How many of those stars do have planets like Earth? On how many of those Earth-like planets did life actually develop, and so on.
If you're an optimist, you find that there are lots and lots of intelligent communicating civilizations in our Milky Way galaxy. If you're a pessimist, however, you can easily find that only 1 in a million galaxies like ours might have intelligence. So if you're a pessimist, we may well be the only ones in our Milky Way galaxy.
If a massive and malevolent alien force heads our way, what is Earth's best defense?
One of the things that saves us is space travel is slow. We'll have warning that they're coming. We'll see them with probably many days warning as they pass through the solar system looking like another giant asteroid or comet coming in from the outer solar system. As they get here, the question is, what do they do? Are they really the Independence Day aliens that come in and sit over our major cities and threaten all life as we know it? Or do they simply land and offer us their books and their medicine?
If it becomes a street fight, perhaps Earth will be saved using weapons inspired by science fiction. From Luke Skywalker's elegant lightsaber to the laser guns used in 1,000 Saturday matinees, there's no shortage of handheld weapons in sci-fi.
Weaponry in science fiction for years has had some sort of stun setting. The phasers in Star Trek, the staple guns in Space 1999 will render somebody unconscious but not kill them. Technology today is getting better at that sort of thing.
Inspired by science fiction, weapons researchers continue to develop a variety of ways to affect someone's behavior without blowing a hole through them using a crude projectile.
The U.S. military have developed the active denial system, a system designed to elicit the goodbye effect. What this is a huge microwave transmitter. You shoot this to disperse crowds, people literally feel like their skin's on fire and they say, goodbye.
Other military projects harness the power of electricity, building on taser technology to deliver a non-lethal jolt. A simple phenomenon, such as electricity, of course, is science fact. One that has sparked many ideas in science fiction, including providing the power for one of the most famous time machines ever built. Have your 1.21 gigawatts standing by, fire up the flux capacitor, and get ready to take a trip back in time. Time travel. It is possible, according to two of the 20th century's greatest scientific minds, Albert Einstein, whose famous equations did nothing to preclude the possibility of time travel, and Dr. Emmett Brown, inventor of the flux capacitor. The big difference? Einstein's time machine only goes in one direction and is supported by mounds of scientific evidence.
We know from special relativity and general relativity that time travel is absolutely possible. Time travel to the future. If you traveled to a nearby star at a sizable fraction of the speed of light and came back, you would find that people on Earth have aged a lot more than you have.
Relativity actually allows time travel forward. Buck Rogers in the 25th century got it right, Andromeda got it right.
Doc Brown's time machine goes both forward and backward in time. And according to the laws of physics, that's a no-no. Or is it?
Traveling into the past doesn't seem to violate any fundamental laws of physics. And in fact, there are some schemes that physicists have talked about that seem to provide an opportunity to travel into the past. Traveling in a certain way around a black hole might do it. Wormholes could conceivably be converted into time machines. If you take one end of a wormhole, accelerate it to close to the speed of light, send it out many hundreds of light years, then bring it back to close to where you started, well, that end of the wormhole exists permanently in the past of the other end. So presumably, by flying through the wormhole, you can travel into the past.
Sounds simple, but scientists say there's no known way to stabilize the energy field that would make up such a wormhole. And another problem. Travel to the past, and you risk causing a paradox.
The grandfather paradox in time travel is that you go back in time and kill your grandfather before your mother or father was born, and this then means that you couldn't have possibly come into existence. But then how could you have gone back in time and killed your grandfather? It's a logical paradox.
Other people have said, well, you know, maybe there's a way around this problem. There is a way of looking at quantum mechanics called the many worlds interpretation of quantum mechanics.
One of the many interpretations of quantum mechanics says that every time a decision is made, the universe splits. Every time I send a photon of light through a slit and it goes in one direction, there's another universe where it goes in another direction. Every time I spill my coffee in this universe, there's another universe where my coffee remains safe. According to this many worlds interpretation of quantum mechanics, anything that could have been has happened somewhere, and anything that can be will be somewhere in the multiverse.
And so there are literally countless universes splitting off from our own every second of every day of every year. And if that's the case, then people argue that, well, traveling back in time, you could go back and kill your grandfather, and you'd still be alive. Well, how is that? Well, you just traveled into a different universe.
If time travel is possible, one thing is certain. It's going to take a lot of energy.
In Back to the Future, Doc achieves time travel when he gets his DeLorean powered up with 1.21 gigawatts and achieves a speed of 88 miles per hour. That's all just complete fantasy. The actual energy required for travel backwards in time, that is, travel faster than the speed of light, is infinite, or even more than infinite from what we can tell, or requires some sort of a wormhole or other passage, shortcut through the universe. 1.21 gigawatts just isn't going to do it. 88 miles an hour just isn't going to do it.
Sometimes movie science trumps science.
What is a flux capacitor and how does it work? You know, I have no idea whatsoever.
The Back to the Future trilogy also shows flying cars speeding down aerial highways in the now not so far off year of 2015. Many tales of science fiction miss the mark when it comes to predicting the future.
One of the amazing things about going back and looking at old sci-fi is people never really imagined how integral a part of our lives computers would become, how all of us would have our own handheld devices, our own laptops, our own desktops, and everything we do would, in many ways, be mediated through the technology. Even small children now have their own laptops in many cases. And you don't see this in the sci-fi.
But in other ways, the distinctions between the worlds of science fiction and science fact are becoming more and more blurred with each passing year. After all, Kirk and Spock aren't the only ones with a pocket-sized communications device that can connect you with anyone else on the planet.
Bormanis to Grazer, come in.
Under the topic of communications technology, excuse me. Not now, Andre, I'm busy. Communications is a place where science has outpaced science fiction. The cell phone that flip open like the original communicator actually have more options than the communicator did. I mean, did you ever see Mr. Spock playing Tetris? Did you ever see Captain Kirk interrupted by a text message? No. Science trumps science fiction. Who'd have thought it?
What seemed miraculous 40 years ago is carried around in our pockets today.
Science fiction is the dreaming side of science. It's the imagination. But you can't have science itself without imagination. Science needs inspiration. It needs that eureka moment, that aha. And I think science fiction helps create those moments for scientists.
With each passing decade, creators of fantastic tales of the future push the imagination further. Because man will always wonder about tomorrow, even after it arrives. A paradox befitting the intertwined worlds of science fiction and science fact.